Tonight, I'm sharing with you a $25 million math lesson for free. I'm not selling anything. I'm simply trying to help you understand how to use the high school math you've learned to have a healthy financial future and share with you information that I dearly wish I understood when I was your age. The other day, I explained this to an 18-year-old, and she said to me, Kennon, this is the cheat code to life. So as always, I'm here to help you improve your SAT score. I've created 13 questions tonight to help you, and I want to make sure that by getting that good score, it helps you save lots of money in college. And tonight we're looking at exponential models, which I call the most useful math in high school because it's how you actually learn to manage money. And I'm also going to be showing several examples on how to use the Desmos calculator on the new digital SAT. All right, let's take a few moments to try this problem on your own. As always, tap pause and try it on your own. You'll learn a lot more if you try it on your own first. All right, as with all SAT questions, we start with asking ourselves, what's the most important word? And this question looks confusing. There's, this equation. We've got A's and B's. Well, B's mixed in here. But at the end of the day, it comes down to what's the most important word. And in this problem, it's the y-intercept. And as I've said in many of the other videos, the y-intercept is the value of y when x equals 0. And they're actually telling you to do that right here. They're saying, hey, put in 0. If you'll just put in 0, you'll actually figure out what b is, and then you'll know the value of b. So that goes along with these three strategies, which is what I call the ordered pairs in disguise. Don't just stare at ordered pairs and just plug it in, okay? So here we've got the 0. We're telling you to just plug it in. So if we go to our equation and plug 0 in for x, we can work it out. Now, of course, we've got to follow the order of operations, so be very careful here. You're supposed to do exponents first. Do you recall what 3 to the 0 power is? Well, it's just 1. In fact, anything to the 0 power is 1. And this is something that shows up on pretty much every SAT. So try not to forget that anything to the 0 power equals 1. So this would be 5. That changes to 1. And then we can do 5 plus 6 for 11. Okay, so that should have been 11. Now, let me show you quickly how to use Desmos to do something like this. So you can type your equation into Desmos, and this one, maybe it was called f of x. You could call it g of x. It doesn't matter, but don't type in y. Make sure you type in like an f of x or a g of x here. And then since we were trying to find a y-intercept, we're just putting a 0 into the equation, and Desmos tells us we should get 11. So even if you goof up and you forget that anything to the 0 power rule, maybe you can use Desmos to make sure you get it right. And of course, the other thing that's wonderful about Desmos is it does graph for you. So you could just look at the graph and see that it's 11. So keep in mind, silly little mistakes like anything to the 0 power equal 1 can really goof up your score. So Desmos is a great way to double check. All right, let's take a look at our next problem and tap pause to try it on your own. Well, this is just some basic vocabulary. First of all, hopefully you understand this graph is definitely a decreasing graph. If you're not aware, you should read math just like you read English, which means you should be reading from left to right. So if you were a marble and you were trying to roll along this graph, you'd definitely be going down. So this is decreasing. It is not going in a straight line. So this is known as a decreasing exponential function. All right, let's move to our next problem, and I'll give you a few moments to tap pause and try it on your own. It says, which of the following would be an increasing exponential function? Well, one of my sayings is tables make great giraffes, or tables make great graphs. So if they give you a table, maybe we should just plot those points. Now they are looking for an increasing function, so let's look at these numbers. I mean, they're definitely increasing. These are increasing. Okay, they're all increasing, so darn, we can't cross anything out, but we could go ahead and just start plotting the points. So we've got -1, 8, and then 0.16 and 124. Well, if you look at these and then the next one's 32, that really makes a straight line. Okay, and if you find the slope, you can see that these are just increasing by 8. So that's going to be a straight line if they're all going by the same amount. And you know, here these are also just going up by 1. So that's not looking too good. If we plotted them out, I think we would see that maybe it's something kind of slow growing actually. Here, if you look, these are getting multiplied by 2. And if we take a look here and put one at 4, then 8, then 16, and then 32, do you see how like this grew a little bit, this grew a lot more, and this grew a whole lot more? Well, that's an exponential graph, okay, because it's starting to pick up speed. And that's why this sort of math is so important for your future, because when you save money, you don't want it to go up at a straight line. You want it to start going up and going faster and going faster and going faster. And that's what exponential functions do. And that's why we're going to show it at the end, where I try to show you how to make $25 million by just using only 50,000. All right, let's tap pause and try this next one on your own. So here we've got a bunch of weeds out in a yard, and it says that they double every 10 days, okay? And it says currently there's only one weed in the yard. So we've just got that one. So we might make a little table here and say like the time and then the number of weeds. And so we're starting off today and we have one weed, but then it says every 10 days it's supposed to double. So I'm going to be counting by tens. And if it doubles, well, then we're going to have 2 weeds after 10 days. That's not too bad, right? But then those 2 weeds double, and now we have 4. And then those 2 weeds double, and we have 8. So these weeds are starting to grow kind of quickly. And I'm trying to show you 360 days, which is about a full year. So if we needed to figure out, well, I probably don't want to count by tens all the way to the end of the year, do I? So let's write an exponential equation to do this. And oftentimes they use the letter P in school. Oftentimes they use the letter A on the SAT. So I think I'm going to switch to A. But this A is your starting amount. And we are starting off with just one weed. And then B is known as your base, which is your multiplier. And in this case, because the number of weeds we're doubling, we're going to be timesing by 2 every single time. So our base is 2. And then our exponent, well, because we're counting by tens, we are actually going to double the number of weeds 36 times in a year. Okay? And so if we follow the order of operations, we have to do the 2 to the 36th power. And luckily for us, we started with just one weed. But oh my gosh, look at this. We would end up with 68 billion with a B, weeds. So that's an important lesson. Make sure you don't just ignore your weeds. You got to go out there and pull them out or kill them some way. And it's also a very important lesson because what if this was the amount of money in your bank account? And what if you could double the money in your bank account? Can you see that eventually if you keep doubling things, they get really big really fast? So this doubled just 36 times and you all of a sudden had 68 billion weeds. So exponential graphs, extremely important because they can take off super fast. And if you do your finances right, maybe your finances might look like these weeds someday. All right, let's try our next problem. So in that last problem, we kind of introduced this formula where you've got a starting amount and a base and then the time. And this problem goes along right with it. Let's kind of dissect everything here. So we've got 64 donut holes that somebody left in the teacher's lounge, okay? And then they snuck this word in here. It says the half-life of the pile of donuts is 12 minutes. So if we were to make a table here, we would say like, well, when somebody dropped off the donut holes, they dropped off 64 donut holes. And if we came back 12 minutes later, then there would only be half of the donut holes still there because it's a half-life. So there would only be 32 donut holes. If we come back in another 12 minutes, half of those are still there, so 16. And if you've ever noticed, I don't know if you've ever watched like a hidden camera, but if you have a big pile of something in the break room, some people might take 2 or 3 or 4, but once that pile starts to get smaller, people usually only pick like 1 or 2. So that's why maybe these things aren't disappearing quite so fast. But then after 36 minutes, you'd be down to just 8 donut holes. So that's maybe why a lot disappear early and not so many later. But hopefully you're seeing kind of how the half-life pattern works. And if we were to make a graph of this, we would see, we start at 64 and then quickly break that in half and jump down to 32, and then 16 and 8, and then 4 and 2 and 1, and then eventually you have to break that one in half. So exponential not only can grow, but they can decay, but it still creates a curve. And there's a nice pattern. We're chopping everything in half. It's just not a linear pattern because it's a different amount every time. So let's look at these equations. You can see the 64 out in front. So they're all the same for that. And, it is a half-life problem. So we're going to be timesing by a half. We're not going to be timesing by 2. The part that gets tricky is it says, well, okay, how many are going to be there after t minutes? Okay. So if we were to put in 12, okay, we could try putting a 12 in here, a 12 in here, and a 12 in here. Because these all look very similar, but we got to somehow spot which one's going to be right. Well, if we do 1/2 to the 12th power, that means that we're going to chop this pile of donuts in half 12 times. There's not going to be a lot of donuts left after 12 minutes. If we put a 12 in here, well, that's going to be the 144th power. So that's going to be even worse. We're going to chop this pile of donuts in half 144 times. Whereas if you put a 12 in here, 12 divided by 12 is just 1. So that means that our pile of donuts would get chopped in half just 1 time. And that's what we would want to have happen after 12 minutes. So the SAT has very common questions that look like this and are multiple choice. And the best way to sort out like the right answer when all these exponents are different is pick a good number to put in for the time, and then you can do the work to check the answer. Now, I'm going to quickly show you how to use Desmos to do this as well. And, people just don't think about how to use Desmos enough. And Desmos is the calculator that's included in the test now. So it's really an important tool to get used to using. What you can do on a multiple choice question is you can put all the answers in there. And so if t is supposed to be the amount of time, and I try this first equation, you can see that, like after just like 2 minutes, it's already down to 16 donut holes. And it's not supposed to be down to 16 donut holes. So we say, okay, maybe that's not the right answer. Let me try the other one. Well, gosh, that shows that after just 1 minute, we're already down to less than 1 donut hole. That sounds like the teacher's lounge I used to have. And then here's a different one. But what this one shows, if we zoom out a little bit, is you'll see, it is an exponential curve. It's definitely got a curve to it. And if I come out here to 12 minutes, you can see that it's pretty close to, there we go, 32 donut holes. And that's what we expected. And we could try the last option, and you can see, well, that one's actually growing, and we definitely do not grow donut holes. They always seem to disappear. So it's kind of neat that you can just kind of compare the different answer choices and look for which one's right. And a lot of times using Desmos is actually faster than just doing it by hand. I love it if you could know your math and think it all through, but sometimes it's nice to use this powerful tool. All right, let's try our next problem. Please tap pause and try it on your own. We're starting with 50, so these all start with 50, and it's doubling. Okay, so these should all be 2 because we want it to double. And then it's doubling every 20 minutes. So we're getting kind of excited in the last problem we put in a 20 and this became a 1 and everything worked out. But uh-oh, I've got some bad news. The SAT has underlined a word, and whenever they underline a word, that is the most important word, and you better think long and hard about how that word impacts this problem. So they want you to do this equation in hours, but they gave you this information in minutes. So we've got a little bit of a problem here. So what you might want to do is, like I did in the last one, pick a number and put it in. Now, we would not want to put in 20 anymore because that would be 20 hours. Okay, so if we did put a 20 in here, then that means that after 20 hours, it would have doubled one time because this would just be 1. So that's not going to be correct. Now, if we were to put a 20 in here, okay, that means that it will double 400 times. That's kind of interesting. We might want to take a look at that. What if we just picked 1 hour? Let's think about that. Wouldn't that be an easier number to use besides 20? So if I put a 1 in here, that would mean that this would double, but it would double 20 times in 1 hour. Does that make sense? I hope not. It's only supposed to double every 20 minutes. All right, what if we put a 1 in here? All right, that means that it's going to double, but it's only going to double 1/3 of a time. So it hasn't even doubled in an hour. Okay, that doesn't sound right, because if it was supposed to double every 20 minutes, shouldn't it double 3 times in 1 hour? So if we try putting a 1 in here, well, that would be 3. And that means this would double 3 times. And that's what we would expect in 1 hour. So D is going to be the correct answer. Again, you could take all the answer choices and put them in Desmos and take a quick look at them and compare. And so what I did is I said, well, let me check in this first equation how many there would be after 1 hour. And to me, there shouldn't be just 51 bacteria after 1 hour. But I could try this equation after 1 hour. And that came out to be millions and millions of bacteria. That didn't sound right. And then 62 bacteria, and then down here 400. And that 400 is happening because it doubled several times. And we could take a look at that and say, like, okay, well, after 20 minutes, it doubled once to 100. And then after another 20 minutes, it doubled to 200. And then after a full hour, it doubled to 400. Okay, so lots of different ways to use Desmos. You can use it to help you evaluate functions really quickly and try different numbers. Okay, let's go on to our next problem. And please tap pause and try it on your own. So also a very common style of question, these best interpretation of questions. They do these for lines, exponentials, and quadratics. So be ready to do one of these best interpretation of problems. This is what I call an ordered pair in disguise. Some people have a hard time reading f of x notation or v of x notation. All you really have to do is write this as an ordered pair, and that's just saying that when you put in 0, you got out 3.8. All right, let's take a moment to read over the problem. It says the number of new viewers in millions of a viral video, W weeks from. So they like to do this. What they're saying is that this equation is only valid for the first 9 weeks where the video is out. But generally, this sort of stuff is not super important, and try not to get fixated on that. I see a lot of students who just stop doing a problem when they see that because they don't know what to do with it. That's not the most important word. So skip that and go down to your ordered pair. So what this is saying, and a couple other things to do too, you can look for the meaning of the variables here. Okay? So if you're not sure in a word problem, we've got V of W, and we have W. And just write out what they are. So it says W weeks. So I know W is weeks, which makes sense because W starts, or weeks starts with W. And V, well, I don't know, V, that might be something. So V is the number of new viewers, okay? So it makes sense. Sometimes they make the letters actually match up. So then if we look at our ordered pair in disguise, what it's really saying is that when our X value, which is our W, when our weeks is 0, the number of new viewers is 3.8 million. Okay. And then we can go and look at the answer choices and try and figure out what's going on. So, would there be initially 3.8 million viewers? Will there be 3.8 million viewers in 45 weeks? Well, no, this is saying that there's 0 weeks, not 45 weeks. There's 3.8 million more viewers each week. Well, this isn't saying the number more viewers. It's the... and it's saying each week, where this is saying, no, this was in the first or the 0 week. And then here, I don't know, this is talking about months. Well, this problem's not about months, it's about weeks. So it kind of looks like there was initially 3.8 million views of the video. And as we've seen in the other problems, this starting number here is the starting amount, and that is the initial amount. Okay. Yep, there's just a good way to break down word problems. It comes in handy on lots of different questions. If you don't know what the variables mean, write out a quick little summary like we did down here, and then hopefully you can find the values for them, and that'll help you better understand what to do next. All right, by the way, I did want to introduce myself really quick. My name is Kennon. I founded Transformative Tutoring in 2018. In the last 5 to 6 years, I have done over 10,000 sessions helping students with math. I must love math, and I certainly love my students. So it's been a wonderful 5 years. I am a former high school math teacher. I've helped numerous students get perfect 800s on the math test. I've helped about 20 students become National Merit Scholars. I am extremely proud of the fact that my son is a National Merit Scholar, and I'm extremely happy that he was able to go to college on a full ride thanks to being a National Merit Scholar. And he is extremely happy because he actually goes to school 100% for free, and he actually gets paid over $10,000 a year to go to school. So we never thought that you could actually make money going to college, but he did so well on the SAT that he actually gets paid to go to college. So that should hopefully be a really big motivator for you to grind down really hard and work hard on this test and study, because it truly can pay off, saves you and or your family a whole lot of money, and maybe even makes some money, which we never even thought was possible. All right, let's try this next problem. Tap pause and try it on your own. We're starting to get to the main focus of this video, which is what we're talking about exponentials. I'm trying to help you with the SAT, but we're starting to talk about putting money away. Here we've got somebody starting off with $10,000. Hooray! Once you get your first real job, and you're going to see in a few moments why it's important to save money early, you should find a way to set aside $10,000 a year. That might sound like a lot right now, but once you start getting a real paycheck, it's like $200 a week, which I know sounds like a lot right now, but trust me, I'm going to show you in a few minutes that it's really worth it. And so in this problem, we're using compound interest, which hopefully you did a few of these problems in school. And unfortunately, when you take money and you just drop it off at the bank, they're like, hey, thanks. And then they give you some little crummy interest rate like 1.2%. Okay. So they want us to set up the equation for this. Now, to do this, first of all, you need to take the 1.2% and change it into a decimal. Anytime you need to turn a percent into a decimal, you just divide it by 100, which is going to move the decimal place over 2 places. So really 1.2% is 0.012, which is not a big number, is it? Okay, about the number of brain cells I have some days. Okay, now what we're going to do is use an equation to try and figure out how much this is going to be worth in the future. Now, if you take $10,000 and well, first of all, this is just the wrong number. Let's just cross those out right away. We are looking for something that has one of the 0.012s in it, okay? Now, if you think about multiplying something by 0.012, is that going to take your $10,000 and make it bigger or smaller? That's definitely going to make it smaller. So this is not a good thing, okay? But what would happen if you took your $10,000 and you times it by 1. What would happen? Well, you'd still have the same $10,000, wouldn't you? So, yay, at least you didn't lose all your money, because that's what happened right here. It would all pretty much disappear. But if you actually want your money to grow, you have to multiply it by something bigger than 1. And here, the Scrooges at the bank are just giving out a little tiny interest rate. So you're going to multiply it by 1.012. Okay, and then that's to the t power. And the rule is you always take the starting amount, which we might write as p or we might write as a, and then you're going to go, and you're probably more familiar as a p from school, and you're going to go 1 plus the rate that it's growing to the t power. Now, really quick, I've got a little bonus question for you here. It says, how much would the deposit be worth after 39 years? Well, that's the beauty of algebra, is you can write equations and then you can plug numbers in equations and work it out. It turns out that after 39 years, you would have $15,000. So think about that. Is that a good trade? Would you like to give somebody $10,000 today and come back 39 years later and they hand you back, pretty much close to $16,000, okay? Would you take that trade? I wouldn't. I don't know what, the concert tickets are going to cost in 39 years, but I've got a feeling that the $10,000 I have today would be better off spent today than waiting 39 years to get $16,000 back. So a lot of people think that by putting money in the bank, something good's going to happen. Almost nothing happens, okay? Almost nothing. This interest rate is extremely important for your financial future. And when you're working to set up yourself for retirement and to have large amounts of money in your savings, you have to be very aggressive to try and increase this number as much as possible without doing anything ridiculous or illegal, okay? But the percent of interest is really important, because you don't want to come back 39 years later and basically find out you had just about the same amount that you started with 39 years before. All right, let's take a look at another problem. I'd like you to tap pause and try it on your own. Okay, so very similar problem, but now we're heading in the opposite direction. We have something depreciating, okay, which means it's going down in value. And unfortunately, I see far too many people get their first job and they go out and get like a great truck or something. Well, I certainly didn't do that. And anybody who ever worked with me kind of knew what my car looked like in the parking lot. But I did it for a reason. And hopefully this problem will help you understand why, okay? They want us to come up with the right equation. And, we're starting with a $50,000 truck. So we know that's going to be $50,000. But it's depreciating, which means the value of the truck is going down. And you all know that if you buy a new car, it's going to be worth less the next year and the next year and the next year and the next year. And it's just going to keep going down until it's almost worth zero. In fact, I took my car to a dealer the other day and they did offer me $1,000 for it. So maybe that doesn't go down to zero, but it goes pretty close, okay? I decided to keep it because I knew the tires were worth at least $1,000. But anyways, the car or the truck is depreciating by 19%. So first of all, if it's depreciating, do we want to multiply by something bigger than 1? I don't think so. That's going to make it bigger, right? So these two are automatically out. Probably should turn the 19% into a decimal. Well, if you just divide it by 100, you're going to get 0.19 just by moving the decimal over 2 places. Now, stop and think about this for a minute. If you took a test and you missed 19% on that test, okay, this is kind of mediocre, but how many did you actually get right? Well, you got 81% correct, okay? And that is kind of how this depreciation works. The value of your car disappears, but you still have the other part remaining, okay? And so if you lose 19%, you still have 81%. So that's going to be the correct equation. This would be really bad. That would mean that almost the entire amount would be gone after 1 year, because there'd only be a little tiny sliver left. So just like in that last problem where we said like the future amount is going to be the starting amount, and it's going to be 1 plus the rate to the t power. Well, if you have something that's going down, I don't think you get to add the rate. You have to minus the rate. So in this problem, we're doing 1 minus 0.19, which is going to leave you with 81%. So if you have something going down, just try to think about if you were to miss that many points on your test, how many points would still be remaining? And that's going to be your multiplier. Okay, as a bonus question here, we're going to take a look at the value of that truck after 9 years. And so if we simply put a 9 in there and work it out, we're going to find out that our $50,000 truck is now worth $7,000. So that's kind of a bummer. You bought it at 50 and now it's worth 7,500. And guess what? You're going to have to turn around and buy another one. And so then you're going to be out another 50 grand. So be careful when you're excited with your first new job. Maybe you don't want to go out and buy a brand new truck. Maybe you want to save your money, because I don't think every 9 years I want to be dropping 40-something thousand dollars on a new car. All right, let's try our next problem here. Okay, well, this is decreasing by 40%. So imagine that. You took a test, you missed 40%. Uh-oh. All right. Well, hey, good news. You did get 60% right. Okay. So we definitely would want to have a multiplier of 60%. But now what do you got to do? Well, we've got this information. Well, these are ordered pairs in disguise again, right? So if we turn this into an ordered pair, it's the ordered pair 316. Don't just stare at ordered pairs. What do you do with them? You plug them in. So we're going to plug a 3 in, and we're going to hope to get out 16. Well, if you put in the 3, what's 3 minus 3? That's just 0, right? And what's 0.6 to the 0 power? Well, as we saw earlier, anything to the 0 power is just 1. So this would become 1, and we'd have 250 times 1, which is definitely not 16. But I hope you can see here, when you put the 3 in, that's 0. Anything to the 0 power is 1, and we get 16. And that's what the ordered pair was telling us. When we put in 3, we're supposed to get 16. Okay, a lot of these different questions are all written in very similar ways on the test, and they show up in all sorts of different topics. So be ready for those ordered pairs in disguise. All right, while I've got you here, I would like to please ask you to subscribe to my channel. It lets me know that you're watching and that I'm helping you, and I really appreciate it when people subscribe. Please do know I have several other series out there. I've got one on common SAT mistakes. I sit here and help students every day. I kind of repeat myself because it's the same mistakes every year, every day. So if you watch some of these videos, maybe you can prevent yourself from missing some mistakes and get it right the first time when you take the test. I also have a series on the hardest digital SAT questions. I went through the 20 most difficult recent practice problems released by the SAT for the new digital exam, and I break those down. If you're trying to get a great score, please watch these videos. It'll make a huge difference and show you some of my secrets and tips. All right, I'm also working on a hardest solve series where I'm going to try and go through 100 of the hardest problems from the older SAT. Trust me, they're the same type of questions. As more and more people are looking at these videos, I'll try and create some of those for you as well. I also have a nice comparison between the classic SAT, that's what I call it, versus the new digital SAT. So if you got questions like, oh, how's the test work, blah, 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 please check out these. Maybe get a couple laughs along the way and learn a few things about the ins and outs of the test. All right, tap pause now and try this problem on your own. Okay, so a very common style of question. These are called transformation questions when you start seeing things like this and they're trying to move the graph around on you. So it says that the graph of f is drawn, okay? The graph of f is shown here, so maybe put an F on that. And it says which equation could model g, so that's a graph we're not seeing, and they say that g is equal to f of x plus 2. Now, it's very important on these transformation problems. Please study them. They are all over the test these days. You know, there's only 44 questions now, so if there's like 2 of these, that's pretty important. if it's on the inside, it's actually going to move the graph left and right. I like to say inside moves side to side. But the thing that tricks most people, and that's why I've got this caution symbol here, is it moves in the opposite direction. So if it says x plus 2, it's actually going to move to the left and towards the -2. So what we might do is we might take some points from this graph and move them over to create a new graph. So just kind of taking this and moving it over to, take this, move it over to, and so forth. Take this and move it over to. Okay, and there's our new graph. Okay, now a couple things you should always focus on. If you're kind of stuck on a graphing problem, I would really encourage you to look at the y-intercept first. That is like the most important point on most graphs, unless it's a parabola. If it's a parabola, it's probably a vertex. But look at the y-intercept and think, okay, well, the y-intercept looks like it's like 0.30 something. Well, look at these equations, These are starting at 16 because this is the starting amount. And these are starting at 36. So I'm pretty sure we can narrow it down to one of those two. Now, the other quick thing you can observe about this is, if you multiply something by 0.75, is that going to make it bigger or smaller? Well, that's going to make it smaller. So really a 0.75 graph is going to be heading down and be a decay graph. So if you multiply something by 1.5, well, that should make it get bigger. And so it definitely has to be D. Now, other things we could try and do is, grab a different ordered pair from here. And that's where people kind of struggle sometimes. They don't understand that graphs are really just lots of ordered pairs. And I'm not sure any of these look particularly awesome, but what we can do is we can take these equations into Desmos, graph these equations, and then try and compare them to this graph that I moved over to. So I've got the 4 different equations, and here's something that I did that was kind of cool too. I plotted out all the points from the actual starting graph, okay? And I just looked at the ordered pairs based off of the graph, and then you can actually type ordered pairs right into Desmos. And then what I did is I shifted all of those points over 2 units to the left because of the x plus 2. And then we can try the different equations. So that was answer choice A, and you can see it hits a point here or there, but it doesn't really match the graph. And then there's the second one, which actually matched the original graph. So yay for that. And then here's the one that was a decay. And then here is the one that hits all those points perfectly. So if you really, really want to work hard at this, you can actually type the ordered pairs in and see which graph goes through all the ordered pairs. And of course, if you didn't type in the ordered pairs, you could still look at the graph and go like, like this looks like it's going through like around 2 and 81. Yeah, there it is, 2 and 81. And then you could look at the graph in the problem and see if it matches. And of course, here you can see like the y-intercept at 36. So then you could match that back to the graph that you have. Okay, so pretty cool. You can get ordered pairs plotted in Desmos. All right, let's try this problem on your own, please. Tap pause now. I see the 0.96, that, or the 0.94. That to me tells me I took this test and I got a 94, which means I missed 6%. So we're not going to have 94% of the population leaving. We're only going to have 6% of the population leaving. So those are out. It does say, like it's got this t over 10, and it says t years after. So what we could take a look at this and say like, well, would it be 6% leaving every year or 6% leaving every decade? So if we were to try like 1 year, then this is not going to cause that full 6% to leave because that's just a 1/10 power. But if we put in 10 years, then we would have the 0.94 one time. And so that means that every decade we're going to lose 6%. Okay. Hope you're starting to realize the importance of like picking your own numbers and putting them into Explore a little bit. All right, before we head to this final problem where I'm going to show you how to turn $50,000 into $25 million, and I'm going to talk about it in depth a little bit and cover lots of different things. I want to remind you, please practice. My son did, this little pile of problems, and it helped him earn, about $40,000 to $50,000. That's a pretty good deal. Please use the Blue Book app to get used to the test before you take it. You can download it and start practicing using this website right now. There's 5 practice tests available, 1 PSAT and 4 SAT, so please take a look at those. Please take one moment to subscribe. I would sincerely appreciate it, and don't forget to like this video. So here's what I've been leading up to all night, is trying to show you what we're about to do. So I've been looking over this problem for a few days, and I thought to myself, like, okay, the idea is we're going to put in $50,000, okay? But just as something simple that I could get on the screen, I'm trying to show you like $50, okay? And what if I could get you to take $50 and turn it into $1,000? Does that seem like a pretty good deal to you? I mean, I think anytime I could pay somebody $50 and get back $1,000, I'd be pretty happy. But the technique I'm going to show you today is going to take that $50 and turn it into $25,000. But you don't have to stop there. The way math works is if you add a few zeros on here, you add a few zeros on here. So actually, this technique is not going to teach you $50. It's going to teach you how to take 50,000 and turn it into 25 million. Okay, and we're going to just be using the same math that you've been using in all these other problems. So what I've done, and I'm going to show you the name of this fund in just a moment, okay? But there is a fund that I invest in, and lots of other people invest in as well. Hold on one second here. That has produced very nice results for a long time. And, yeah, darn it. Okay, there we are. Okay. And I looked at the history of it, and it was created 39 years ago in 1985. So that's why in that earlier problem we did 39. So we took the $10,000, we earned 1.2%, and it became $15,000 39 years later. So I want to show you what happens if you can earn a very high interest rate here, okay, of 16.31%. So we'll set up our equation. We'll have our 10,000 that we're starting with, and then we're going to go 1 plus our interest rate because we want the money to grow, and then we're going to put it in for 39 years. Okay, if you didn't already tap pause, and I'm sorry I forgot to hit that. If you didn't already tap pause, please do so and give it a try yourself. But I think you're going to be amazed to see that $10,000 can become $3.6 million. Now that is just one $10,000 deposit growing to be $3.6 million. So what I thought to myself is like, well, if I could take 10,000 to make 3 million, maybe I shouldn't just make one $10,000 deposit. What if I made $10,000 deposit on 5 different years, okay? And so what I thought is, okay, most people when they're done with college, they're 22 years old, and everybody talks about retiring at age 65. So that's a difference of 43 years. So if you put money in at 22 and then you retire at 65, that's set for 43 years. But you also could put money in when you're 23 years old. That would take 42 years until you become 65. Or when you're 24 years old, 25 years old, and 26 years old. Oops, 26 years old. So these are the first 5 years after college. And what if you put $10,000 in for each one? So what I did is I created a spreadsheet that analyzed all of this, okay? And we've got a $10,000 deposit starting when you're 22 years old, starting to take money out when you're 65 years old, never putting in any more money ever again. So really at this point, all you ever did was put in $50,000 and you get that 16% return. Well, the money that was in for 39 years is going to be $3.6 million. We saw that already. But the money that you put in that very first year when you were 22, that sat in there for 43 years. And you can see the difference from 39 years to 43 years. It went from 3.6 to $6.6 million. Now, the reason why this is happening is because this interest rate is so insanely large. Okay. And if we take this money from the 5 different years and add it up, it's $25 million. Okay. Now, I set this up as a spreadsheet so we could try some different analysis. So, like, what if you waited until you were 32 to put in your $10,000 for the first time? Okay. So if you were 32, the money's not going to sit there as long. Can you guess how much money you're going to get if you do this? Well, you're going to end up with $5 million, $5.5 million, which is obviously not bad. But if you're going to put in $50,000 sooner or later, wouldn't you rather just put it in right away and get 25 million instead of 5.5 million? Okay. Now, the other thing I looked at is like, well, what if you just put in $10? You know, because a lot of people are like, Kennon, I can't do $10,000. Well, just put in $10 the first 5 years. Let's see how much that becomes. Just putting in $10 5 times, that's $50. Your $50 became worth $25,000. I'm pretty sure you can find an extra $10 every year to put into a savings account. So what if you did $100 a year? Well, all of a sudden you're talking about $250,000 just for putting in $500. What if you could do $1,000 a year? All right, now you're getting to 2.5 million. So understand, you know, maybe you don't think you can do $10,000 a year, but even anything, even just $1,000 5 times could lead to $2.5 million. That is insane. And I hope that gets you really excited to start saving money. What I also thought is like, well, sometimes your employer matches your money and maybe gives you like an extra, the way it worked for my job was an extra $3,000. So, you know, if I were to put in $13,000 a year, I would end up with 32 million. Now that's just 5 times. That's it. And never putting in another dollar ever again. So then I thought, well, okay, most people probably can't do the 13 grand, but maybe if the employer kicks in 3, they make it there. But you know, once you start saving, it's kind of like addictive. You're like, oh my gosh, this is really working. So maybe you don't stop after 5 deposits. Maybe you do like 10 more years of deposits and just do an extra $2,000 for those extra 10 years. You know, let's see what that does. Well, that makes you an extra $6 million. So, you know, just if you don't even stop investing, you just start putting in just a little bit, you can still make a huge amount of money. All right, let's take that back off and just understand, you know, here's our basic scenario. But look, if you go and you get like 2% interest, you know, all of a sudden your $50,000 is only worth $112,000. What if you got 10% interest? Well, that would be pretty nice. $2.5 million. It doesn't exactly match the 16.31 we had and the $25 million. So finding an interest rate is really an important part because that's something that doesn't cost you anything. You know, yes, you still have to put in the same amount of money in all these plans, but if you can get that higher interest rate, that's where the big numbers come from. Okay, so a couple other things I want to mention. What if you make the mistake of waiting and you only start to put in money when you're 40 years old? Okay, and you still want that $25 million because you're like, Kennon showed me how to make $25 million, so I want to see. So let me go in here and show you something called Goal Seek. So what I want to do is I want B14 to still be $25 million, but I want to do it by changing B1. And so what this is if I waited until I was 40, okay, you can see the 40 up there. If I waited until I was 40, I'd have to put in $151,000 a year for 5 years. So that's $750,000. I mean, it's pretty hard to save $151,000 a year. But that's what it would take in order to still end up with $25 million. So please do not wait until you're 40 to start saving, because it's kind of getting to be a little too late at that point. You've got to do it. Here's one other thing. Let's pretend we went back to the 10,000. Okay. And now imagine if you start today. What if you started when you were 18 years old? How much do you think it's going to jump from 25 million to what? Well, $45 million. What a difference 4 years makes. And it's because it's the 4 years at the beginning, because once that curve starts to go nuts, it goes nuts. So maybe you can find a way to start saving money right now. Okay. I hope that really helps you. I want to show you some other information because I'm not a financial advisor. Okay. You should consult a professional before investing. Past returns do not guarantee future results. You know, it is possible to lose money when you're investing. So you cannot just simply take crazy Kennon's math tutoring service here for advice, but do your own investigations and learn about this on your own, and take a moment to do some research. Okay. And so here's some things that I did to do some research. Here's just a picture of this fund, okay? And this is the fund that I've used in the past, and I find it extremely helpful. It's made a huge difference in my life, and you can see how towards the end here, this thing is really starting to take off, and it looks gradual here, but it was really still growing. It's just that these numbers are nothing compared to how big these numbers are. And why, you know, they started it in 1985, and because it's gotten that 16%, you can see the actual, this is based off of stock market information. So the actual amount that $10,000 put in 1985 grew to 3.45 million. So it's pretty close to what this was. What I also wanted to show you is that this FSCXS, which is a Fidelity fund, okay, and I don't work for Fidelity. I'm not asking them to pay me anything to say this stuff. But there's many other funds out there. And here you can take a look. Like in 2022, it actually lost almost 30% of its value. And you can see it up there in that chart. But what you can also see is that there's other funds in this category, or it's compared to an index. And so like, even though it lost 29%, it was actually in the 18th percentile. It was one of the better funds out there that year. Whereas some years, like here, it's kind of in the bottom half. It's the 69th best fund in its category. You can see last year it made 51%. So if you can imagine basically taking whatever money you have, chopping it in half and adding that on to how much money you have, you're like, oh my gosh, that was pretty insane. So you can see some years are good, some years are kind of average, some years you can lose a lot of money. So be aware that you can lose money in stocks. Be aware that there's other things. Like here, you can see they only made 8-something%. They were in the bottom quarter of all the other funds. So there's plenty of other funds out there, and I encourage you to go out there and investigate. But that's the one that have experience with, so I thought I'd use that in this example. Okay, and I think that's pretty much all we've got there for you. I want to thank you for watching. Next week, I'm talking about parabolas. It will not make you $25 million, but I hope tonight's did. And I look forward to seeing you in the future. And please take a moment to like and subscribe and watch some of my other videos.